Hello, welcome to my channel. Today we're going to be discussing depth first search. You're probably here because you've looked around and are still searching for a good material on this algorithm. I'm going to try my best to explain it on an intuitive level. Depth first search is an algorithm. From the name depth, it's a graph traversal algorithm. So you use it to visit nodes in a graph and take action depending on what your goal is. So from the name depth first. So depth doesn't necessarily mean horizontal depth, like the height of a tree. So it can be either in any direction, basically. So on the left hand side, you can see the depth, the first depth is going to be right with this algorithm if that's the way it's implemented. So basically, if you're going right first, it's going to traverse every right side of the graph, or like in the example of this array. And then when it's done, it's going to pick the next direction. So if your next direction is left, it's going to go all the way left. Not all the way left, sorry. So it's going to go left and then probably back down and then right. So it's more intuitive with a tree. So here we have a tree. On the left image, there's a down arrow. So basically, such algorithm would have been implemented with a right first approach. So from the three arrows in the left image, it traverses from the root all the way to the right bottom node. Then back up, traverses the left of this node, and then right again. So long as there's a right unvisited node, it is going to be traversed first. On the left hand side is the opposite. So it's going to traverse all the way left, then back up, and then right. So it's going all the way right because there are no left nodes. So I'm just going to do a little demonstration of how this traversal is going to work. So here we have the root. So on the left hand side, we have the left first, a depth first algorithm. And on the right hand side, we have the right first, depth first algorithm. So both are starting at the root. They are not exactly identical trees. I've done this for a purpose. So now it is going to choose the right node on the right side and the left node on the left side. If this is a bit confusing, please just you can follow each photo at a time. Then the right first is going to traverse the right node first. The left first is going to traverse the left node first. So all that doesn't matter here. It all depends on what you're trying to achieve. So left is gonna go left, right is gonna go right. Now watch what happens on the left hand side. It's going to go right because there are no left nodes. So there you go. And then now it's backtracking. These nodes have been visited. So it's going to go all the way back to whatever parent node has an unvisited node. So there you go. Traversal. Now right is gonna go right. Left first. Okay, it's not at the parent node of the two bottom nodes yet. So right's going right. Now left first. is going to go left, and then the right node. So that's the end of traversal. Now I'm going to apply this depth first search to this LeetCode problem. This LeetCode 199 binary tree right side view. Sorry guys. So the problem is, given the root of a binary tree, imagine yourself standing on the right side of it. Return the values of the nodes you can see, ordered from top to bottom. So in this example, the tree is actually represented as an array or as a list if you are using Python. So I think what this does is, in the background, it constructs a tree with the input. So for this, the height is 3. You can see the arrows are pointing at the nodes that are visible from the right side. So what we're trying to achieve is a depth first algorithm that is going to return the right side view of a tree. Here is my solution to this problem. I'm going to advise to, whenever you face a problem like this, some people advise to go straight to the solution if you can't figure it out. I've done that in the past, but later I just realized I wasn't really getting any better. So I just got better at looking at solutions. So then I took a different approach, and there's been so much more progress. So try your best. Try your best to come up with this solution, or at least do a good bit of work. That's how you build the intuition for such problems. So this is the algorithm. This passed with 0 microseconds, so among the top performing algorithms. So what was the strategy? Strategy was, as listed on the right side, created a dictionary. That's the res variable to update view and depth. Then make the algorithm go right first. So when you go right first, you are trying to figure out the depth of the right hand side, and then use that depth to update the view list. That way you can only add nodes that are lower or deeper than the depth of the right side. And then we're going to return this dictionary to the left side, and the left side is going to update using the value of depth in the dictionary. And when done, we return the view, which is going to be the list containing the values that we can see from the right hand side. So what I've done here, if you look at the code, down the bottom, I'm returning the actual view while I'm returning the dictionary. While I'm returning the dictionary at the lift nodes. So the reason I've done this is I try to challenge myself. So what I do lately with LeetCode problems is try to not create a new function inside of the solution. So I try to adapt. It forces me to think and come up with ways, and it improves your Python skills as well. So right here, we are looking at the strategy for solving this problem. So we have a dictionary to update view and depth. So on the left hand side, you can see I've named it RAS, raise. Then second strategy is go right first. When you always go right first, then you are updating based on the depth of the right hand side of the tree. Then add nodes with depth greater than the current depth. Pass this dictionary from the right hand side to the left hand side. So when you traverse the right, you update depth, and then when you return or backtrack, if the left node is unvisited, then you pass this. So to maintain the depth information, to update, here's the strategy for solving this problem. Feel free to pause the video and take a look. So here I've marked out the nodes that are included in the output in green. So the tree has depth of 3 in both the right hand side and the left hand side. So in this case, we are returning only nodes 1, 3, and 4. And I'm going to take you through the algorithm step by step. So this is the start. You call right side view, passing in the root, 1 and none. You have to be very careful when you use dictionaries, lists, and other reference variables. They behave inconsistently, and please, you want to be careful. So best practices suggest you set it to none and then initialize at the call of the function. That's what the line there is. So if not res, then set it with a depth of 1, and the view, you add the value of the root node to the view. So right here we call the function with our initial arguments. So we call right side view, passing in the root, depth of 1, and none. So it is best practice that you use none, set them at none for default arguments for reference variables. Their behavior can be very erratic. So I've actually spent a lot of time on a solution only to discover that my problems came from not setting that value to none. So I would advise you always do that. So in this case, we call right side view, passing in the root. So the root gets visited, like you can see on the right side, on the right image. So this value gets added to the view. Now the root is going to call node 1. We call the function. So the function is recursive. We call it with a depth of 2 and an updated view. Node 3 does the same, updates depths so far, adds 3 to view, calls the function recursively with a depth of 3 and the updated view. This continues. Node 4 updates the dictionary, depth 3, an updated view. Then 4 calls the function recursively again, but this time nothing happens because this node doesn't exist. That means the right and left nodes are none. So now it's going to backtrack. Now node 4 returns res to node 3, which in turn backtracks to node 1. Now this time node 1 has left node, which is untraversed. So this information will be passed to node 2. Node 2 receives this, checks the depth is not higher than depth so far. So does nothing, calls, and mind you, depth at each node remains the same. So the function argument remains the same. So from the code, you can see the function argument remains the same. Node 1 is going to call the function with a depth of 2. So 2 does nothing with it because it's not as deep as the current depth. Oh, sorry. It's not actually deeper than the current depth. So nothing happens. Calls recursively again. Node 5, nothing happens. Node 5 is not deeper than node 4. So depth 3 is maximum. Now backtracking. The call returns with same information back to 2. We backtrack back to node 1. Here we are done with traversing. Now the depth at this call is actually 1. So that's the last if statement in the algorithm. Now node 1 is going to return the result, and that is the solution. Guys, please, this is my first instruction video. I want feedbacks. I've never done such a thing in my life before, but I've faced problem trying to find solutions or explanations of certain things, and I've had trouble with them. So I just thought I probably might be able to explain a bit better. So your feedback is welcome. I'm gonna try and put out 1 to 2 videos a week. So please bear with me. This is a new territory for me. Thank you for your time. If you have any questions, please drop a comment. I will address every question. Also, suggestions are welcome. There's a problem you want to be explained, I am willing to do the work, try solving it, and then present a slide. Thank you very much once again. Have a good day. Bye.